In this video, we want to learn how to find a general rule for higher derivative of a function f(x). In general, in order to find a general rule for higher derivative, we need to find out what is its pattern when we take derivatives. But in order to find the derivative, to keep the pattern, normally you have to be very careful. Don't try to make any change after you take derivative. So let's take a look at a specific example. So f(x) equal to 1 over 2x minus 3. Normally when you see this, you want to say, okay, if I want to find a derivative, I want to use quotient rule. But if you use quotient rule, that's going to be much more complicated each time you take derivative. So instead, what we try to do, we actually rewrite this function as 2x minus 3 with -1. So in this way, we can actually apply the so-called generalized power rule to find its derivative. So now let's take a look at the first derivative. The first derivative, because you have generalized power rule, basically says if you have u of x raised to n, its derivative equal to n times ux raised to n minus 1, then multiply the derivative of the inside. Okay, that's so-called generalized power rule. So now, for this case, the u equal to 2x minus 3. So the n is -1. So now, when we take derivative, just follow this rule here. We're going to have -1 and 2x minus 3 and n minus 1, which is -1 minus 1, which is -2, and 2x minus 3's derivative inside function's derivative. So that's 2x minus 3's derivative is 2 there. So you can see you have a -1 and a 2x minus 3, -2 times 2. Okay, remember we mentioned earlier, we want to keep the number, don't want to change this number. If you multiply them together, you actually cannot see the pattern anymore. So that's the reason, don't try to multiply those numbers. Keep the number as it. Okay, so now let's take a look at the second derivative. Second derivative, so here, second derivative, so that's those coefficients just keep as it. But what we have here, that means I'm going to take derivative just to that thing here. I copy the -1, and that thing here, I take derivative, use generalized power rule. So here, now the n is -2, so I have a -2 and 2x minus 3, -2, which is n minus 1, so you got -3. And so here, then you have to take 2x minus 3's derivative, and that's 2. That thing derivative is 2. So you have a -1, -2, and a 2x minus 3 to the -3rd, and a 2 and a 2. So you have a 2 times 2. So, okay, so here that's second derivative. And so now let's look at the third derivative. And those things here just copy down. And this take derivative from, again, from this generalized power rule, I'm going to have a -3 and a 2x minus 3, and -3 minus 1 is -4. Again, the inside take derivative, you're going to get another 2. Okay, and now, by now, pretty much you already see the pattern there. Okay, take a look here. And when you have a third. You have -1, -2, -3. You have 1, 2, 3. That's 3 2s. Okay. When you have a second, you got -1, -2, and you have a 2, 2, 2 squared. That you can see this is 2 to the third. This is 2 squared. Okay. And so here also you look the exponents there. If this is 2, this is -3. This is 3. This is -4, which means you're gonna have negative. That number is one more than your derivative. So with this here, now we can definitely generalize the following rule. The nth derivative equals -1, -2, because that's 3, that's -3. So that means you can imagine that's n, that's got to be -n, and 2x minus 3, negative, that's a 4, that's 3. You see that's 2, that's 3, which is always one more. So you're going to write this as m plus 1, -m plus 1. Okay. And you can see that's 3, that's 2 to the third. That's second derivative. You got 2 squared. So that's nth derivative. You got to have a 2 raised to nth. Okay, so that's giving you its general rule. But if you want to make the general rule looks a little bit nicer, you actually can rewrite that thing here. Okay, what do you have here? Because -1, you can see each of them contains -1. So you can write this, have -1, how many of them? N many. After you put all the -1 together, you only have 1, 2, 3, all the way to n. Okay. So remember this, you can rewrite this as n factorial. So we want write this is a little bit nicer way, nicer looking. So here we can write this -1 raised to n and times 2 raised to n and times n factorial and 2x minus 3 raised to -n plus 1. That's give us the general rules here. So you can see in order to find the general rule for a function's higher derivative, normally you have to find the patterns when you take derivative. The good ways to recognize the pattern is when you get the numbers, make sure you don't multiply them together. Imagine you multiply together, you got this here. That's one, okay, you got -2. Next one, you're gonna have -8, a +8. And the next one, so here you're gonna have more numbers here, and you will not see the pattern there. So if you keep the number untouched, then you can see the pattern. Okay, so that is a function, okay, algebraic function. And similar for a trig function, you also, when you take a higher derivative, you also need to do the same way. So here, let's take a look here. Fx and its first derivative equal to sine's derivative, which is a cosine 3x. And remember here, since this sine, the argument is 3x, it's not x. So you have to multiply the inside derivative according to the power on the chain rule. So that gives us 3, that's 3 cosine 3x. Okay, so let's look at the second derivative. And 3, okay, keep not change. But the cosine derivative is negative sine. Negative sine. So negative sine and 3x. And again, the 3x derivative, which give another 3. Okay. So you can write this as 3 squared. But now you got a negative sine 3x. Okay, so now let's take a look at the third. Third, you have what? And 3 squared negative sine derivative is cosine. Same thing, the 3x take derivative, generate another 3 here. You have a 3 cube negative cosine 3x. And the fourth, so I have a 3 cube cosine take derivative, which is negative sine. Again, the 3x derivative, you get another 3 there. So you have 3 to the fourth. Okay, now you can see that becomes a positive sine 3x. And it seems here we still don't have the pattern there. Let's take a look one more. To the fifth x. Okay, so you're going to have 3 to the fourth times cosine 3x sine 3x, the 3x derivative, you get another 3. You got a 3 to the fifth, okay, cosine 3x. And to the sixth, and I have 3 to the fifth, negative sine 3x. And I get another 3. So here I have 3 to the sixth, negative sine 3x. Okay, so let's check the pattern now, okay? So you can see here, what do you have here? Now, the second derivative and the sixth derivative, besides this 3, the coefficient different, but the function part actually same, okay? But if you look the first derivative and the fifth derivative, beside the coefficient part, the function part are actually same there. Okay, so if you do the seventh x, then you're gonna get 3 raised to the seventh, okay, and negative cosine 3x. So which means what you have here, the third derivative and the seventh derivative, beside the coefficient different, so the function part are always same. So you can imagine, so here, now, if we have any function, so here, say if I have f, okay, raised to the 25th x for this case. So I'm going to have, you can see, 7th, that's a 3 raised to the 7th. 6, okay, that's a give you 3 raised to 6. And but if you have 25th, so I have 3 raised to 25th. But the question here, what is this function? Is that sine or cosine? Is it positive or negative? Okay, so now we actually got to see the following, okay? Because the function, you can see the first derivative got don't look at the coefficient, okay? Just look at the function part, okay? You look, first derivative cosine, second is negative sine, and the third is negative cosine. Fourth back to the same as original sine, 3x, beside the coefficients, okay? But the coefficient we don't need it, we don't care. So now we only look the function part, the trig function part there. So means when you do this, when you continue do this, so here you can see the eighth derivative can be 3 raised to the 8th, that back to the sine 3x. So which means every 4 times you back to the original function beside the coefficient. So now, so here means when we do this, all I need to do, look here, and the number divided by 4. So here I have 25 divided by 4. So here, like this case, I get 6, 24 as 1. So that tells us that the remainder is 1. So that tells us what you have here. That's going to give you the first derivatives function. Don't look at the coefficient. The coefficient is already done. So here, the first function is a trig function. So which means because that's 1, that's just same as the first derivatives function. So here, that's going to give you cosine 3x. Okay. And so here now, if you say, how about f raised to the 37 derivative? Same thing here. You use 37 divided by 4, okay, and 4 times 9, 36. The remainder is 1 again, okay. So that's give us 3 raised to 37 and sine and 3 cosine 3x, because remainder is 1, so that means just like the first derivative trig function, which is cosine 3x. Okay, and we do a different one. So here, say how about 40 9. 49 is actually same. 47 divided by 4. Okay, remainder is 3. So the 47th derivative gonna be, okay, 3 raised to 47. Because remainder is 3, you look, that's going to be same function as third derivative, same trig function. So here you're going to have negative cosine 3x. Okay, so that's how we find, let's use general pattern there. Okay, that's the end of this video there.